today with us, we have Tom McGuire with Maxcom. Tom's been an SCT member since 1994 and very involved with the chapters throughout the years, as well as being a national board member from 2003 to 2006. And we appreciate your time today, Tom. So I will hand it over to you, sir.
Great. Thank you, Vince. And I appreciate the opportunity. We're going to cover DOCSIS 3.1, DOCSIS 4.0, extended spectrum DOCSIS, the 1.8 gigahertz testing solutions and validation. And again, appreciate the opportunity and for all of you to take the time, and hopefully you'll get some benefit out of this if you're involved at all in extended spectrum DOCSIS upgrades. So we're going to start talking a little bit about the competitive landscape, because obviously a lot of decisions that we make in our business is based on obtaining customers and retaining customers. I think a lot of that plays into what we're talking about here with what's going on from a competitive standpoint. We'll touch on what is extended spectrum DOCSIS. We're going to talk about the different splits, your standard sub-split, mid-split. There's a high split. There's also a Euro split that would be considered similar to what the traditional US sub-split has been, just a little bit higher frequencies. We're going to talk about why would a cable operator consider doing extended spectrum DOCSIS, and we'll talk a little bit about the existing HFC plant overview, um, and current PON deployments, greenfield versus brownfield. We'll get into that because it obviously makes some differences as to how your network is set up as to what path you might want to go. We'll talk a little bit what's required to do an extended spectrum upgrade. And, there's a lot of equipment that's swapped out, but there should be a lot of validation that goes in there as well to determine whether or not, you need to replace some of that equipment, which could contribute to some of the savings that you would experience, but being able to offer higher speeds for your customers. So, what is that testing required? We'll go through some of the validation of the existing devices and cable and talk about some tools that are available in order to do that. We'll talk a little bit about the cost savings versus a PON upgrade, kind of review the components for each technology and repair the costs. And we'll wrap it up with a little ROI and a summary of what we've covered. So, just to state, if there are any questions, please use the chat box. Vince will be monitoring that and interrupt at any time. I want to make sure to answer any questions that you may have. So, with that, we'll launch into the competitive landscape. And, traditional cable MSOs are seeing competition from a variety of sources. And most of these other competitors have launched a pure fiber network utilizing some type of PON technology. The Verizons out there and some of the different telephone companies that had their old copper networks. That copper had to be replaced with fiber, so a lot of them are doing fiber to the home. And I think what's happened is there's generated a belief within the common consumer that, oh, if I don't have fiber to the home, I don't have a good network to watch TV, surf the internet, do my streaming. And that's really not the case. And those are some of the things we're going to dive into here, and how you can overcome some of that perception that's out there. Um, of course, the big element for a PON network is that they theoretically will offer symmetrical speeds for the downstream and the upstream. And that's one of the issues with a traditional cable network is while you might be able to deliver 10 gig downstream, the upstream has always been a limiting factor. Even though the upstream is not as it's needed, but the downstream obviously is most of what people are doing when they're, streaming movies and all of that type of thing. Uh, so today, a traditional cable network is using what's called the subsplit of 42/54, and get into that differentiation in a minute. And you're typically only able to achieve upstream speeds of about 50 megabits per second, while your downstream speeds are easily exceeding 1 gigabit per second or more. So there's a couple of different things that are happening in the return path with like the OFDMA carriers, along with moving your return path to a higher bandwidth, and even the remote PHY nodes that are being deployed. That's what's allowing the operators to close that gap between the downstream and the upstream speeds. So if we look at extended spectrum bandwidth overview, we'll start in the upper left corner. You can see the subsplit, and the blue bars is representing the upstream frequencies. So as I mentioned, the subsplit that's been deployed for many, many years now is 5 megahertz to 42 megahertz for the upstream. And then your downstream is 54 megahertz to, some systems are still operating 750 megahertz. The standard many years ago became 870 megahertz, but a lot of systems have deployed out to 1000 megahertz or 1 gig. So the downstream has a little bit more flexibility from that standpoint. And as I notate there, the green bars represent those downstream frequencies on the graph. Now, the Eurodoxes, I just threw this in for an education point, but their upstream has been 5 megahertz to 65 megahertz, and then typically the downstream is 112 megahertz to 858 megahertz. So one of the things, just to back up, when I said that subsplit and I had like the 42/54, when they represent that, like the mid split is represented 85/105, there's that gap between the upstream frequencies and where the downstream frequencies for different parameters, and I'm not going to like FM, that type of things. So the mid split, as I mentioned, is 5 megahertz to 85 megahertz on the upstream. And then your downstream is moved from 105 to 1 gig, or actually, you can go out to 1200 megahertz as well. But the high split is taking now the return path from up to 204 megahertz. And then the downstream starts at 258 megahertz out to 1200 megahertz. But again, a lot of systems are deploying out to 1800 megahertz for the downstream. But then the ultra high split, you're now taking upstream from 5 megahertz to 684 megahertz. And then your downstream is extended all the way out to 1794 megahertz or 1800 or the 1.8 gig. So that gives you a good graphical representation of what these different, the mid split, the high split, ultra high split looks like on the frequency chart. The one thing that I failed to do, and I don't remember off the top of my head, is there is a chart that can show you what you can anticipate with respect to maximum downstream and upstream speeds. But with the high split, they're typically, theoretically, you can get at least the 10 gig downstream, and the upstream is not, may not be so symmetrical, but in discussions I've had, some people are getting up to that 7 or 8 gigs. So they're, you're definitely closing the gap as you deploy the extended spectrum DOCSIS. So why extended spectrum DOCSIS? And as I touched on earlier, the fact is there's millions of miles of existing coax plant out there. While the HFC network has been around for many, many years now. It's probably early 90s when, fiber started being used into, going to nodes and then reaching the traditional coax network. But, what's happened is the hybrid fiber coax network, fiber has definitely been being penetrated more and more through the years. And but the issue is that there's still a lot of coax in those last miles from the nodes to the end user. So there, probably 8 years ago, there was a focus on a node plus zero technology, and but again, due to costs and that type of thing, and as technology has improved over the last 8 to 10 years, you can get by with a node plus three amplifiers or even more, but still utilize extended spectrum DOCSIS and that existing infrastructure to deliver the speeds. Because what it comes down to is the customer internet demands. 5 years ago, 6 years ago, we had a lot of transition of people working from home. That's kind of become the mainstay now. And if you're working from home, you need a really good internet connection. The other thing is the plethora of streaming applications that have been deployed. And as we all know, over the last couple of years, there's been a lot of talk about AI and the fact that that's just going to consume even more bandwidth. So it's going to require networks to have as close to symmetrical speeds as you can get, with the symmetrical services being downstream speeds equaling your upstream speeds. And we circle back to the competition out there on the fiber to the home providers touting these symmetrical services, and trying to give that perception that a traditional cable network can't meet that. And the reality is, and I heard a great ad for a cable operator talking about their fiber powered network, which is 100% accurate, because at the end of the day, there's still a lot of fiber deployed within an HFC network, but the coax will deliver the speeds that you need with a lot of these upgrades and extending that bandwidth. So just a quick touch on DOCSIS 3.1 versus DOCSIS 4.0 standards. I would say most locations out there, if not all, have upgraded and they're DOCSIS 3.1 compatible. The DOCSIS 4.0 is the new standard. It's been around for quite a few years, but not a lot of locations have converted to this standard. And I think there may be a perception out there that extended spectrum DOCSIS is only related to DOCSIS 4.0, but that's not the case. If you've got DOCSIS 3.1 in your plant, you can launch extended spectrum DOCSIS and see significant value from doing either a mid split or a high split within your plant to get more of those upstream speeds. The one thing I want to touch on with the DOCSIS 4.0 is there's the full duplex DOCSIS, which basically allows you to use upstream, downstream, same bandwidth. But there's obviously a lot of other challenges associated with the full duplex DOCSIS. Again, it's one of those decisions as you look at your network, you have to determine what makes the best financial sense to as to which direction you go for that upgrade. Yeah, because again, there's a lot of options available to increase the downstream speeds. The big bottleneck is the upstream speed. And, extended spectrum DOCSIS is the path to improving those upstream speeds. Okay. So just a quick visual on, what the HFC network looks like here. So, from the optical node, you're feeding your trunk RF amplifiers and bridgers that feeds the passive plant. And again, pretty basic description, but your typical HFC network started where one node would service up to 500 homes. But as people have done node splits and reduced the number of subscribers off of that node, that's helped with their speeds and performance. And like in the node plus zero environment, you're only serving anywhere from 70 to maybe 100 homes off of a node. So it reduces the saturation on that node, which again can increase your performance. Um, so, but there are a lot of networks out there today that still probably have 10 or more amplifiers in cascade. Uh, but again, the direction is to more averaging anywhere from 1 to 4 amplifiers in cascade, even with the launching the extended spectrum DOCSIS. So what it involves in deploying this is obviously your nodes are upgraded to a 1.2 or a 1.8 gig node, depending on the direction you've chosen to go. And a lot of the nodes now being deployed have the RFi or remote PHY technology, which is basically moving your CMTS out of the head end into the node, which again is helping support getting these greater speeds off of the network. So it's not just one thing like replacing your amplifiers to get these speeds. There's a lot of different factors, the OFDM and OFDMA carriers, the remote PHY nodes, all of that combination is allowing you to get the speeds that your customers want. And once you replace the nodes, then you come in and all of the amplifiers are upgraded to either 1.2 or 1.8 gig amplifiers. And there's a lot of determination. Oh, well, my active plant's upgraded. We're ready to roll. But then there's the question of the rest of the network, which is all of those passive devices that are out there, your taps, your coax, the splitters that are out there, directional couplers, and as these networks have evolved over the years, there's a lot of equipment that's been working very well for the last 30 years that's still out there. And a lot of that has to be replaced. How do you identify it? The flip side is how do you determine whether or not it does need to be replaced? So, as we prepare the plant for extended spectrum DOCSIS, validating coax cables response. And there's a lot of networks, actually worked with a customer that had a lot of 412 cable in the ground. And that's a real expensive proposition to have to go out there and replace all that underground cable. They were able to validate whether or not using the signal generator that we'll get into to determine that, hey, we don't need to replace these spans right now. Or, as I mentioned, it identifies that you do need to replace them. You can validate the passives, the response to 1.2 or 1.8. I've got an example we'll show towards the end on some 1 gigahertz passives will actually get you out there pretty close to 1.8 gigs. So the technology and production there, even though it's labeled a 1 gig or 1.2, they very well may work within the bandwidth scope that you're trying to get to. So, but the other thing here that we'll touch on more is validating that all the actives out there have been replaced and with the 1.2 or 1.8 gig. We'll go into this in more detail, but there's a lot of issues with actives not being documented on designs and prints. And I just make a quick note in here on checking for ingress at the higher frequencies as well as lower frequencies. There's other tools out there for that, but that's another thing that can seriously impact, especially your OFDM and OFDMA carriers. So another aspect to consider there. So how do we validate this network? And there's a lot of flexibility. It starts by having an RF signal generator. There's some different options out there that you can use, but in this case here, we're using the RF signal generator that has complete flexibility on your start frequency, your end frequency. So if you look at the upper left corner there, that's an actual screenshot of the display on the device. And you can see the start frequency is set to 700 megahertz. But if your OFDM ends at, say, 780 megahertz, you just go in and you can change your start frequency to 800 megahertz so that it does, when it does the sweep, it's not interfering with all of your existing carriers. Now, if you left it at 700 megahertz and do the sweep, you're going to have a blip roll through your OFDM, but then as it sweeps out to 1200 megahertz or 1800 megahertz, you won't have the interference, but the signal generator is doing a constant sweep. So you could potentially interfere with those signals, which is why it's recommended you just inject beyond your existing carriers. But as I said, the end frequency, it's showing 1800 megahertz, but if you're only going to 1200 megahertz, you can easily change that. The step frequency. So you can go as granular as generate carriers every megahertz from 700, 701, 702, so on, all the way to 1800 megahertz. All that does is just slow down the processing time. But there's options there. You can go 1, 3, 6, 9, or 12 megahertz intervals. A lot of the work we've done in the past, we've just selected 6 megahertz because that's your channel bandwidth anyway. And you're even at 12 megahertz intervals, you're still going to find any suckouts or potential problems in the network. And we've got some examples coming up on that. Your interval speed in milliseconds, 100 milliseconds is the fastest processing, and that's usually what we recommend. But I have run into some of the older signal level meters that they can't quite process at that speed. So if you slow the speed down of the sweep, it just becomes more in line. And again, we'll get into looking at it on your signal level meter, but and then you can do a repeat and just have those signals, and then you can inject at the node and go to your end of line to see those signals and determine whether or not all of the devices will accept the extended spectrum bandwidth. But the other thing you can do is inject into an amplifier and monitor between amplifiers. I've got some examples coming up. I'll show you. There's depending on where you inject into the test port or just outside of the amplifier can impact what you're seeing on the signal level meter. But if you're trying to isolate passive plant, you can inject just between taps and determine whether or not any or all of those taps will support the extended spectrum or not. So we'll get into more on this on how to inject, and we've got some real world examples that we're going to come up with. So, what are the plant impairments that we're looking for? Number one is suckouts, and this is something you can see an example slide here where was doing some work, and you can see that that taller single carrier is from the network because that particular system generated a carrier at 999 megahertz. And obviously, the plant supports that, but you can't see anything beyond that. And in this example, you can see we've got a suck out from about 1085 megahertz out to 1025 or I'm sorry, 1125 megahertz. So there's about a 50 megahertz span there that is you're dropping off the signals. And what that's typically doing is identifying a mechanical or a grounding issue. And I've seen a lot of examples, even in the lower spectrums, like from 800 megahertz to 900 megahertz. Early on, one of my first field trials that I had done, I was still trying to learn how to use the tool, understand what's going on in the network, and we encountered just that that there was a major problem with that device, and it turned out after the fact that that device actually had to be replaced. So the signal generator was able to determine that for you and pick up suckouts within the plant. The other thing is standing waves, which basically just typically will represent an impedance mismatch. But this is on a spectrum analyzer that you can see. And if you look at that trace, you can see that it's just kind of a rolling wave. And that's just giving you an indication that there's an impedance mismatch somewhere. But the big thing, and this is what we're really looking for, is the legacy components that will not support the higher bandwidths. As I mentioned, there's a lot of amplifiers out there that were dropped in, never documented on design prints, and typically the process as systems are deploying and moving forward with either the mid split or high split projects, they're going out there and doing the walkout, identifying all of the equipment that needs to be replaced. But I did a lot of work with contractors that were out there, doing this type of work. And once they did the installations, it would turn out about 1 in 4 of their cuts would have amplifiers in there that were never identified, and the only time they were identified was after the fact, after they activated the locations, and then either the modem not locking up or other issues led them to track this down, which was more time consuming and more importantly, customer facing, which is what we're trying to do with all of this, is eliminate any of the customer facing issues. So but what you're going to have here, and I've got an example slide coming up, but here you can see we're going through an amplifier and you get complete roll off of your signals. And that if a device will not support the extended spectrum, that's what you're going to see, is that type of roll off. Okay. So before I move on, any questions? Okay, great. So So validating the network and using your signal level meter. In this case, I'm showing screenshots of the Viavi ONX signal level meter, but I've got some examples coming up with VX and Divisor. Really, any signal level meter that you have that you can go in and do a spectrum analysis, and it's always best if you can do it on a peak hold, but the any of these signal level meters will work. But the first thing that we do when we go out to support a system looking at these upgrades is take the signal generator and set your frequency range from 700 megahertz to 1200 megahertz, or 800 megahertz to 1200, and go directly into your signal level meter, and you'll see all of your carriers here. And the other thing that I wanted to point out is that all of the carriers are pretty consistent, right around 40 to 42 dBm, plus or minus a couple dB. So um, they are, gives you that nice flat trace across the spectrum, versus like when you're typically going through an amplifier, you're going to see higher levels on the higher frequencies. But when we were developing this, it was determined just flat signals across the spectrum was going to offer the most value. So when we look at the network then and we inject into the plant, what you're looking for is a pass like what we have here. And this was a real live demo that we did a few years ago. But you can see here that you've got all of the existing carriers on the lower frequencies from 48 megahertz up to 600 megahertz or so, and then you can see the OFDM carrier that's up there that ends right around 750 megahertz or so. So we want to inject beyond the OFDM so it doesn't interfere. But here you can see we have a fairly nice clean trace, which is telling us that all of the devices between the signal generator injection point and where we're reading the signals with our signal level meter, everything supports the higher frequencies. And what you're looking for is the fail, which is anything that may roll off. And in this case, it's a 1 gig amplifier that we had injected through. And again, to point out, you can see in the middle slide, it's nice flat signals across. But here we went through the amplifier and you can see the slope that was introduced through the amplification of the amplifier, but then the complete roll off. Obviously, this amplifier is not going to support the extended spectrum. Okay. So injecting signals at the node, this was another real life example where I was out in the field, and you can see, I believe that's an Aurora node. This was actually kind of a nice setup because we were able to inject those signals right into the test port on the back of the node. And then on the right hand side, we went to the end of line, the very last tap, off of that leg of the node, and you can see we have complete roll off. So all of that plant was 750 megahertz plant. The other thing about injecting at the test point to point out, so it's going to drop your signals by about 20 dB. So you can see the carriers on the network, and then our the signal generator signals are 20 dB down. Where that can become an issue is if you've got a long end of line and some of those signals may be so close to the noise floor there that you can't make a clean determination. But then you can just inject at some different spots and shorten the distance, like between amplifiers or something like that, that'll help elevate those signals and determine whether devices pass or fail. But the other thing I want to point out in injecting signals at the node, so here's a newer Aurora node that we injected into, but most of those test points have an internal directional coupler, and you're trying to force these signals through there. It wasn't really designed. The test port is really designed to extract the signals where we're doing a blunt injection, and it can provide you some crazy signatures like what you see here on the right. And again, I go back to you, if you do your baseline measurement with the signal generator in directly into your meter and you see a nice flat profile, then anything you get like this is telling you that there's something creating an issue. And in this case, we just needed to inject those signals outside of the node into I believe there was a tap just outside of it, a tap leg that we injected to continue our testing. Okay. Same thing I wanted to talk about injecting signals at an amplifier. So if we inject on the input side of the amplifier, you'll see on the left that we've got nice clean trace, but those signals are actually being amplified because we're going through the processing of the amplifier. And that if it's a 1 gig amplifier, you're going to have roll off like we showed on that previous example. So in situations where you're trying to validate downstream plant, you can inject onto the output side of the amplifier, which is what we did with the right side signature. And I know we already showed this example, but you can see the carriers and the suck out there beyond right around 1100 megahertz. So anyway, again, just trying to share some examples that where you inject the signals can have an impact on your output. But I always reference go back to your reference trace because that's going to show you that you're getting the right signals across, and anything else you find in the plant is something that's creating that issue, whether it's an impedance mismatch or what have you. And again, just talking about some field results experienced, just wanted to circle back on the screenshot here because again, there's a lot of thought out there. Well, hey, I've got a single carrier out there at 999 megahertz. I don't have a need for anything else. Well, that one carrier is not going to show any suckouts that you may be having that's related to grounding issues and that type of thing, where having some type of sweep like this is going to help you identify any imperfections within the plant. And then we all already talked about the uh, seeing the devices that don't support and this was really an interesting case. So one of the very first trials that I ever did, we did a bunch of testing in a lab, and then this particular location had just upgraded to the 1.2 gig amplifiers, and they had 9 end of lines, and they went out there and validated all of the end of lines. And one of them, they got roll off just like you see here, and they worked their way back and discovered that amplifier that was not on the print. So, in this case, they were able to identify that amplifier and get it changed out before activating the plant. But that's the thing in a lot of cases, you're not going to be able to identify it till it's customer facing. So being able to go out there and proactively identify, and as I mentioned, feedback I got from the field was probably 1 in 4 locations have that type of situation. And I can tell you, every system I've gone into and talked to, everybody validates that fact that there's devices out there that just aren't documented, and those are the ones that are going to bite you and become a customer impacting, potentially customer losing problem. So being able to proactively find them is very beneficial. So I touched on the testing to 1800 megahertz as well, and that's definitely the direction that everybody's going. And the signal generator that I've been showing you goes out to 1800 megahertz. And here's some examples showing you exactly how it performs. So as I mentioned, I was doing some training and evaluation. And we've thought, hey, let's pull this Antronics 1 gig splitter. And we ran it out to 1800 megahertz, and if you look, you can see a nice clean trace of all of the signals out to about 1740 megahertz. If you see that red dot on the top part of the spectrum there, and you can see in red, it's showing 1740.67 where our marker is at. That's when we started seeing roll off on the device. So I use this as an example that as you're going out there and doing validation, you can really save a lot of time and money if you don't have to replace devices, but more importantly, validating what does need to be replaced. And then another example that I have of where we did some testing in a head end, or I'm sorry, a training facility where we were testing out to 1800 megahertz. And in this case, we've got the divisor spectrum analyzer there. This first trace you can see, we injected directly into the spectrum analyzer, and we've got that nice clean trace through the full spectrum. So then we found a section of plant in the training room there that there were 3 taps in cascade. So we injected into the tap, and then we're measuring off the port, and we're getting this really funky kind of signature, not quite a standing wave, but not a clean trace. Well, what we discovered is that that last tap wasn't terminated. Once we put the terminator on there, we cleaned up the issue and we had a nice clean trace. So again, it was a really valuable exercise to show that if you're developing or if you're out there and evaluating devices, if you've done your benchmark, anything that you see that's abnormal is going to be related to something in the plant, even if it's just, like I said, the impedance mismatch. Okay. All right. So let's just roll into the cost comparisons for extended spectrum DOCSIS versus PON. As I mentioned earlier, if it's greenfield and brand new plant, just about every operator out there is deploying some type of PON, whether it's 10 gig EPON or XGS PON, which is the next level up from 1 gig PON. Uh, but because there's no existing plant, you're able to cost effectively deploy the fiber to the home network. Where we're talking about extended spectrum DOCSIS upgrades is in what we call the brownfield environments, where you've already had that existing HFC network. And while you've gone out there and you've been able to do node splits and that get fiber penetrated deeper into the network, it's still a huge cost to go out there and upgrade that completely to a PON network. So, and again, this is according to one MSO that I had lots of conversations with, that the extended spectrum DOCSIS is costing about $100 per home pass, where deploying a PON in the same area would be about $1,000 per home pass. And my point here is not to belabor the exact cost, but just show you the actual chasm, I guess, between doing a full PON upgrade versus being able to do extended spectrum DOCSIS and satisfy your customer requirements for their network needs. So the other thing I wanted to touch on is what is your return on investment for plant validation? And this slide here shows you just how significant that the plant validation can be. So actually, it's about 4 years ago, was working with a team that back when we were doing some field trials and had left a prototype device with that group, and they started their project. And about 3 months into the project, I got a call from the maintenance manager who said, "Hey, how do I get my hands on more of these tools? Because everywhere that I go out and use this tool after we've done the upgrade, it's saving me time because I'm able to go out and identify these devices ahead of time rather than after the fact." So they ended up getting some more of the tools, and when the project was done, I went back out and visited with the team, and we sat down and put some actual numbers to and I can tell you up front that everybody that I've discussed this with says that these numbers are very, very conservative, that the actual return on investment is significantly higher. But again, I would much rather take the conservative approach. But for less than a $5,000 investment, the minimum ROI was calculated at over $150,000. So, again, it just goes to show really the issues that can pop up out there, but having a tool to be able to go out there and identify before it's customer facing is really a big advantage. So, in summary, extended spectrum DOCSIS upgrades are taking place with, I think, most of the MSOs I've talked to, and the ones that haven't started doing it are starting to do it this year. It's the fastest, most economical way to offer close to those symmetrical speeds within the network without having to go full pawn network, which is going to cost a lot more. So helps you to bridge that gap over the next 5 to 10 years as that evolves. And as what we've tried to demonstrate, doing some plant validation prior to the upgrade, as well as after upgrading the equipment, will minimize the customer impacting issues. And it allows for faster replacement of the equipment that will not support it. Because the longer you let it go and then you rely on the customers modems not locking in or whatever it is, it's going to be much harder to find those devices after the fact as well. So, wrapping it up, using a signal generator in combination with your signal level meter provides a simple, low cost solution to identifying those devices in the network that need to be replaced.